We finished up the previous video by finding the equipotential surfaces for the electric dipole. And now I'd like to go and get a little more analytical and try to come up with an expression for the electric potential for a dipole at a distance far enough from the dipole that it's large compared to the dipole separation, but not so large that basically the two charges cancel each other out. So we'll go ahead and say that the separation between the charges is D. And we can go ahead and apply our same game plan that we were before. We'll say this is the z-axis. So we need to know this distance here. I'll call that r plus for the distance to the positive charge. And this is going to be r minus, which is, this is going to be r minus, which is the distance to the negative charge. Now the idea is that we're going to be far enough away from the charge that it'll make more sense for us just to use the distance to the center of the dipole, which we will call r. And we'll say that the angle we are off of the z-axis here is theta. So the idea is going to be, we can say, sure, the electric potential will be equal to the potential due to the positive charge plus the potential due to the negative charge. And so we can be all nice and careful about that and say this is 1 over 4 pi epsilon naught. And then here the charge is q and the distance is r plus. And then here we'll do the same thing. And here the charge is minus q and the distance is r minus. And we can clean this up a little bit. We can pull out a q from everything and a 1 over 4 pi epsilon naught from everything. So let's do that. So we'll have a 1 over 4 pi epsilon naught and we'll have a q. And we're left with 1 over r plus minus 1 over r minus. And when in doubt, we can put things over a common denominator. So doing that, we will get 1 over 4 pi epsilon naught q over r minus minus r plus over r minus r plus. All right, and so far everything I've done here is exact. Now here's where the approximation comes in. It's really hard to show in a meaningful way here at this scale, but we can imagine here, if we were to just extend out where our point of interest was, let's say out here. Now if we draw these same lines here, to here and to here, what I want you to notice is that this angle here got smaller and that angle here got bigger. And as we extend it out farther and farther and farther, this angle here is going to get bigger and approach our angle theta. Or sorry, bigger, and this, smaller and approach our angle theta. And this angle here will get bigger and also be approaching our angle theta. So in the limit of being sufficiently far away, what we're going to do is we're going to say that if we're far enough away, these lines are basically parallel. So if we do that, we can then say, all right, here is my, actually I'll just draw it on top of the other one there. So in the limit of being far enough away that I can't meaningfully draw the x to scale here, because here, look, this is like 3 dipole lengths. That's close. But in the limit of being far enough away, where we can say that this angle is theta and this angle is theta, like this. And that means that these lines here now are basically parallel. The extra distance that you have for R minus versus R plus will be the extra distance you have if you drop a perpendicular from Q plus down to here. But this angle right here by construction is also our angle theta. So that means that this distance here is my hypotenuse D, and that makes this excess distance, this R minus minus R plus, the extra distance we have to go from the negative charge versus the positive charge, this is equal to D cosine theta. Or I should say approximately D cosine theta. So now we're going to say if R is large compared to D, we can do two things with our voltage expression. One is we can say that this is 1 over 4 pi epsilon naught Q. Now I have this R minus minus R plus here. That's D cosine theta. And then this R minus and R plus, again, since we're far, they're basically both R. So we can approximate that as being R squared. If you're worried about how much that is, let's just work it out over here on the side. R negative here would be, you said it was equal to R plus D cosine theta. So if I times the two together, R minus, and by the symmetry of the situation, sorry, we can say that R negative is R plus D cos theta over 2, and R plus is R minus D cos theta over 2. So if you times the two together, R minus R plus is going to be R squared minus D squared cos squared theta over 4. And since we said D was really small compared to R, that's basically 0. So it's legit. But now we can look at this and say Q times D, hey, that's the dipole moment. So we can finally write our voltage as being 1 over 4 pi epsilon naught times the dipole moment cosine theta over R squared. Now, unlike when we found the expressions for the electric field, for the dipole moment, we were able to find it everywhere in space as long as we were reasonably far enough away from the charges. And unlike when we did it with the electric field, where we could only find it at 2 points in space. Now, in more advanced treatments, the next step is to then do tricks with derivatives to find the expression for the electric field literally everywhere. So that's a lot easier than trying to do it in general by taking components of electric fields. Alrighty then, so in the next video, we will go ahead and take a look at finding the potential for a continuous charge distribution. See you over there.